Hi, welcome back. Today we have a short video to take a break on our remote control searchlight. You'll see here a quick toy that I'm building for my granddaughter. It's a light chaser. It has 8 LEDs and the lights chase each other in a circle. And so it uses a 4017 decade counter and a 555 timer. And here you see it on the breadboard, ready to go. I'm about to test it, give it a power 9 volts. It'll take a 9-volt battery. To power this, she just pushes the button and the lights chase in a circle. So let's give it a try. There it is. Really cool. So I used the old control panel from the remote control searchlight project. I'll clean up the open holes. Just mounted the LEDs, drilled holes, mounted them, did a quick breadboard job. So why don't we go over the circuit design right quick using Eagle design software. Here we have it. I'm well on the way with a 555 timer schematic and a 4017 decade timer. And what we're going to do is use the 555 to generate pulses, probably around 10 a second, or a pulse every 1/10 of a second, and that will cause the decade counter to go from the first line, powering the first LED, down in sequence through all 8 LEDs. So here you'll see I am just using Eagle software to make the network connections. This is not really going to be an elaborate lesson in how to use Eagle design software. It's something that you can get at a reasonable price. I've used it a number of years. So we're going to connect up the 555 as a astable multivibrator or an oscillator. It'll generate a square wave, and the square wave will go to the clock input of the decade counter. Here you'll see I'm connecting to pin 14, the clock input of the decade counter. Now, with a few connections here and there, we'll be able to wire this up as an astable multivibrator. And you'll see I'm searching for a resistor to put resistors in place. So I'm not going to go through the details of how to use the 555 to design a oscillator. You can look on the web and see many types of web pages that talk about how to use 555 timers in many different ways. Suffice it to say, it's just going to be used to generate a pulse every 1/10 of a second. That will cause the LEDs to move in a circular pattern all the way around about every second. So here we're placing the resistors and doing the necessary wiring to move forward and build the circuit. So we want to make sure we get our circuit design correct first. And one of the interesting things with the 4017 and the 555, you can power it to 15 volts. So I decided to use a 9-volt battery because it's convenient. I could have used a TTL decade counter, but those are restricted to about 6 volts maximum, and I would have had a little bit more trouble um, with the battery connectors, etc. I would have had to have used 3 or 4 1.5 volt AA's or AAA's. 9 volts are just so convenient. So I decided to use the CMOS decade counter on the right, which is the 4017. Here I'm placing the capacitors. I will provide the circuit diagram at the bottom of the video later on, so you can get it and use it if you want to design this and play with it. Here is an important resistor. We're going to connect up the cathodes of all the LEDs on the right through this resistor to ground. And it's important to pick the right value for that resistor in the lower right so that we provide enough current to light the particular LEDs that we use, but also not exceed the current output of the 4017. A few more connections to complete up the oscillator circuit with the 555, connect in the capacitors, and then we will need to go figure out how to choose the right resistor value for the cathode side of those LEDs. The LEDs will only be one on at a time. So there will only be forward current through one LED at a time. So we will need to use LTSpice. I'll show you how to use LTSpice in a really cool way to determine, based on the characteristics of your LED, what the optimum value of the resistor should be. LTSpice is made by Analog Devices, and in just a moment when we finish the circuit design, we will take a look at that, and I will step you through how to build a really cool simulation circuit to give you a graph to determine the most optimum resistor value. So here you will see I'm connecting that resistor to ground, and I'm taking the cathode side of all of the LEDs and connecting them up to that one resistor. As I said, only one LED will be in conduction at any one time, so you only need one resistor in the circuit on the cathode side of those LEDs. So it looks like we're pretty close to having this connected up. Yes, and that's looking really good right now. So what we're going to do is take a quick look at LTSpice and introduce you to that. It's made by Analog Devices. It's a free version. You can get more elaborate versions and figure out what the optimum resistor value will be. So the circuit's pretty much done. 8 LEDs all ready to go. Oscillator, 4017 decade counter in place. And so we could build our actual circuit. So the circuit you saw earlier, we will build from the schematic. We'll use a breadboard, just connect up wire, and just build it up. We're not going to go into the details of how I built that. I'm sure most of you know how to use breadboards and build it. This is more about how to get the circuit if you want to build this. A little bit of an introduction to LTSpice, which is really cool. So let's take a look at LTSpice. Okay, we're going to start up LTSpice. As I said, it's a analog simulation software package that electrical engineers use, and it has a library of components. So we're going to open it up and we're going to throw together a quick diagram. And what we're going to do is we're going to add an LED component. So we're going to search the component library for an LED, and we're going to place it. Then we're going to place a supply, a voltage supply for a DC voltage, and then put a resistor in the circuit. What that will allow us to do is create a simulation to ramp through resistor values for a 9-volt supply, produce a graph to determine the optimum current value based on the average forward current of the LED. And once we do that, we can easily follow the curve and see the optimum value at which we want to drive the diode, the LED. Now, the LED we're going to use has an average forward current of 35 milliamps. I don't run them at 35 milliamps. I run them at half or less. That's very bright. And plus, the 4017 is not going to support driving that much current. So we're going to find the optimum value to drive it at approximately, I would say, 7 to 8 milliamps to 15 milliamps. Optimum, if I was using a TTL driver that could actually source more current, I would probably hit the mid-range between the average, the specified average forward current, and because that's pretty bright on these LEDs for a toy. Now you'll see most people will take an LED spec'd at 35 and they'll drive it right at 35 or the max 35, and they're very, very bright. If you really want a bright indicator, that's fine. I typically don't do that. I typically drive at half of the rated average forward current for the LED. So you'll see I'm setting my 9 volts. And here we're going to actually go pick a diode that matches the LEDs that I will use. And you will see that once we pick this device, we will pick one that has a forward current of 35 milliamps. Here are some LEDs, and you'll see this Nichia has a 0.035. There's several of them here. So there's a 0.035, and it has a breakdown of 5. That perfectly matches the LEDs that I have in my kit. So we'll pick that. Now we've set for the resistor a value of bracket R bracket, and that allows us to change that variable when we create this SPICE simulation. So now what we're going to do is create the simulation logic. So we will go and we will create a SPICE simulation, a SPICE directive here, and we're going to use a parameter that allows us to step through these values. So we're going to step R, which is the variable of the resistor, from 100, I would say around 5,000. And that gives us a pretty good range to see what our current range would look like once we step through that. And we're going to step at 100 each. So we'll step from 100 to 5,000, 100 each time. Now we're going to just do the op command, which tells it do the operation. We'll place the simulation there so we can see it, and we'll run the simulation. You'll see the simulation will run, and it'll pop up another chart. So we'll go and we'll show the values we want to see. So let's look at the forward current through the resistor, and you will see that it will plot the forward current through that resistor. There it is. Now don't worry about directionality here. It says negative, but it's that because of the reverse way I did the circuit. So what we're going to look at here is you'll see there's 35 milliamps at the bottom all the way to the top. Okay, the higher resistor, the lower the resistance, to further left you go, the more current. So we're going to pick somewhere around the middle, anywhere from, I would say, 6 to 15. So you'll see that ends up being a value. If you look at the top as I scroll through this, it's telling you the resistance. So you'll see 380 ohms, anywhere from, I would say, 200 ohms to 400 ohms would produce a forward current through the diode of, anywhere from, I would say, 8 to 15 milliamps, which is optimum. I will opt probably for the lower end of that. So thanks for joining today. You've learned a little about LTSpice. You've learned about Eagle Design Software and how to build a really cool light chaser toy. So make sure you subscribe to the channel, click the notification bell, and please like this video. We'll see you next time.